Next talk will be presented by Bernardo, who will tell us what we can do with logical predicates over types.
All right.
20 minutes.
Yeah, okay. Thanks. I guess maybe the question on your mind when you look at the title for our paper is, okay, why do we need this, or why do we need another fancy type or kinding system in this case? And so our story is that, well, modern software really, if you think about it, often computes with both values and types. And what I mean by that is that often programs use types as actual data, right? So if you have reflection or forms of ad hoc polymorphism, you're actually treating types as a form of data. Or you're doing meta-programming outright, which is quite common nowadays in various tool chains and web apps and things like this. And this is fine. But the problem is that these idioms often, or most likely, move outside the usual boundaries of what type safety gives you, right? And of course, the problem is that we really like type safety, and we would like to have that in some form. And that's why I claim, or we claim, that we do need this kind of fancy kind system. So let me tell you a bit more precisely what I mean by what kind of things I'm looking at. So what I'm going to show you is an idealized version of a function, a generic function, that generates a constructor. So the idea is if you give it a non-empty record type, it's going to build you a function that will somehow initialize a mutable record with fields that are given by the type. So if you have a record person, right, so a record that has a name field, which is a string, and an age field, which is an integer, you would like to have the ability to write this function such that when you apply person to this function, it produces, well, a function which takes, well, a string, an integer, and essentially gives you back the appropriate record. And you'd like this to be type safe for any record type. So essentially what this work tries to do is to have some form of static type checking for these, let's say, highly plastic code idioms, and to do it in a way that's arguably clean, expressive, and more importantly, practical. And because we're people that like type theory, want the type theory to be reasonable, for some definition of reasonable. And so, as perhaps you may guess, our idea of refinement kinds is to sort of lift the idea of refinement types, so it's a natural transposition of this idea to the level of kinds, to classify types. And what this will give us is the ability to write or to specify in a fairly declarative way structural properties of types as these kind refinements. So the key idea is as follows. So everyone knows types, right? So types classify expressions in some way. Everyone knows what types look like. And kinds, most people do know what they look like, so they classify types. So for instance, the type int to int, of functions from int to int, is a type. A record type is also a type. And you can think of, say, list as a type operator of sorts. So list of int would be a type. List itself is a type operator, takes a type, gives you a type. Things like that. So refinement types, most people are also familiar with what refinement types generally are. So they somehow refine a type by essentially you take a value of that type, and not only must it be of the type, it must also somehow satisfy some sort of logical predicate of interest. And in practical settings, usually take some sort of SMT decidable theory for your language of refinements. And so the idea is that your term M must also satisfy this refinement, whatever that might be, as well as be of the appropriate type. So once you do this move, what you get is the ability to write types that look like that. So not only can you write the type int, you can write the type even int, which is the type of, well, all integers that are even, or you can write the type that says these are the positive integers. So you get these declarative properties of the inhabitants of types sort of for free. So what are refinement kinds then? So for me to tell you how this works, I first have to make a little bit of a side move, where not only will I have, say, the kind type, so the kind of all types, I'm going to have sort of specialized kinds that classify types a little bit in a more fine-grained way. So not only is int to int a type, it's also a fun. So it's the kind of all function types, right? And for records, we also have a kind for records. And so refinement kinds are taking the same idea from the previous slide, right? So you take a type, it's of a certain kind, a certain sort of primitive kind, but also you have some sort of logical predicate that you assert on types, right? So it's kind of essentially the same rule, one level up, right? So what does this actually do, right? So the idea is that now we're going to declaratively specify structural properties of these types because they inhabit kinds in some form. So not only is int2int a fun, it's also a fun where the domain type is equal to the codomain type, so it's an automorphism. Or for instance, that record type, not only is it a record type, it's a record type which must have the label name as part of its label set, for instance. So that's the kind of thing that one would like to be able to do. Okay, so what can we actually do with this kind of framework? So I'm going to show you two fairly simple examples because, of course, I don't want to crush you with complicated examples. But to do this, so I'm going to first give you an example, which is, okay, take a record. How can I extend that record? Add a field to a record. So in a generic type-safe way. So in our framework, we also have a kind for the labels of a record. So we can distinguish that. And in terms of refinements, as I've shown you before, we have the set of labels of a record as a way to something we can talk about. And records, so the record type constructor looks like that third item there. So you can think of them as kind of type level lists, except they have the usual constraint that you expect to hold on records, which is all the labels must be distinct. Okay, so if I want to write a type level function that extends a record type, well, it's a type level function. It takes one of these labels. It takes one of these types, or any type, and it will also take a record, but for this to work out in the right way, it must be a record that does not contain the label I'm trying to add to it, right, to maintain the invariant. And it will give me back a record. So what does this function look like? Well, it's just a bunch of lambdas, right? So takes the label, takes the type, takes the record, and it just plugs the thing together, because our system, as you'll see in a few slides, it enforces this invariant by typing or by kinding alone, that the record indeed is only well formed if the labels are distinct. Okay, so how do you do this at the level of terms? So how do I actually add a field to a record value? So you take that type and, well, you write a function. So you write a function that, well, is going to take a label for any type, and for any record that does not contain, for any record type that doesn't contain that label, well, give me such a value, or give me a value of that type t, give me one of those records, and the resulting thing, the resulting record, will be of the appropriate type, right? It will be of the add field type applied to all those things. And so our system does work this out by itself. And if that's a bit confusing, think of it in these terms. So if you take the function add field with the purpose of extending the record just has the age field with the name field as a string, well, you can just apply it to, well, name, string, that record type, and in particular you want to instantiate things with Jack, which is 20 years old. So that will be of the type that's written there, add field type of all those things. And if you compute everything down to values, you'll get the expected record of the expected record type. And it works out nicely. So I kind of promised this sort of generic constructor generator as well. So the one I show, or the one I hinted at, was the one that, if you remember, takes a record type and generates a constructor function for it. So it turns out that's a little bit easier to do if you have some accumulator parameters to this, but the behavior will be as I've described. So how do you write this function? So it's going to take the non-empty record type that you want to generate the constructor for. And what the accumulator stuff is doing is it's, well, accumulating the fields of the record that you've already taken care of, that you've already done something for. And so it takes one of those types and a record of that type. So what does it do? Well, it's going to, well, generate the constructor one by one. So it's going to be a function that takes, a value of the type that's at the head of the record. So you can think of it as a list, right? Because it's not empty, it has a head. And then, well, it depends. If there's more to the record, if the tail is not empty, then we're going to recurse. So we're just going to recurse on the tail, and we're going to use the accumulator to store the fact that we've already handled, let's say, the head of the record. So we add to v, let's say, the head of the label, the head label of the record with the head type of the record. If the record is empty, well, we just put it in v, right? And that's the result, right? Right. So that's the definition of a function. But is it actually well typed? And, well, it is in our system. So it starts, so you type it in this way. So you start with the two record types. And it's going to, well, I'm going to need to use an auxiliary type level function to tell you what the type of this is. But it's going to take one of these accumulator records and it's going to build something. What does it build? Well, it's going to build a function type. And the type is built as follows. So it takes the two records, so the actual record you want to generate the constructor for, the record type, and the accumulator parameter. And, well, it's going to unroll the record S, essentially. So it's going to generate a big function that takes the head type of that record. And then, well, if there is more to that record, it's going to keep doing this. It's going to unroll the tail, put it in the accumulator, and keep going. If we're done, we just return, let's say, the accumulator with the appropriate extension. If that was too confusing for you, this is the behavior of this type level function. So if you give it a record type which has labels L1, T1, and so on, it's going to unroll the record type in such a way that it's going to produce this function type T1 to Tn, and then give you back the record. It's in the reverse order because it's just a little bit easier to do it this way. Okay, so these were the two examples I was going to show you. You can look at the paper for more examples which are a little bit cooler but would take me much longer to explain in ways that you'd be able to understand them in the talk. So we can do transformations to all fields of a record. We can serialize in the generic way a record as XML or JSON if you want to do that. We can type a generic table lookup if you think of a table as a list of records and things like this. So you can do all these cool stuff. So because this is a types talk, right? I'm going to need to show you some typing rules now because that's what the contract says. So first, what does the language look like? So at the level of types, we've already seen pretty much the key features of the syntax, if you will. So we have these refinement kinds, and we have we have dependent kinds as well because we have type level functions which are dependent in some form. The base kinds, I've shown you a few. We have a bunch of them, but we have kinds for records, for collections, lists, functions, references, labels, and polymorphic functions as well. And like I said, we have type level functions, as you've seen. We have actually type level recursive functions, and if you look in the paper, you'll see that these functions must terminate. So there's a sort of simple syntactic check to ensure that these functions are terminating so that the type theory is reasonable. We have polymorphism. We have records, as you've seen in the previous slides. So empty records, non-empty records. And we have these destructor patterns of sorts. So you can take the head label of a record, the head type of a record, or the tail of a record. And we do this kind of game also for function types, right? And indeed for all our type constructors. So the arrow type, TROS, also has, in this case, two destructors associated with it, which allows you to sort of project out the domain type and also the codomain type. And we have a kind case-like construct and a bunch of others, which I won't really cover. You can look at the paper if you want to. And our refinements are fairly simple. So we have these kinds of set-like reasoning about records and labels. So whether a record is empty, whether two things are equal, an interpret equal, whether a certain label is in the record, in the set of labels of a record, whether these are disjoint, things like this. Okay, rules. So you've seen this rule a few slides ago. It's the type refinement rule, but for kinds. So just everything one level up. So it's just that the type must not only be of kind fancy K, but also satisfy the predicate, right? And that's what refinement kind means. Okay. But how do we actually check that these things hold? So there's some basic form on these refinements, on these formula, but that's not too complicated. The key thing, which is done in a few other works of this nature, is to just encode this as a validity check of some SMT system. Okay, and that's what it means for one of these things to hold in our work. Okay, so how do record types work? So the rules are simple. Okay, so all the rule is doing is the non-empty record. The L bit must be a label. The T bit must be a type, right? And the tail of the record, it can be whatever you want, provided it's a record that does not have that label, right, to enforce the label disjointness bit. And if you do that, you have a well-formed, non-empty record. Okay, so the destructors of the record type follow a similar pattern in that the system ensures that while you can only project out the head type and also the head label of a record type if it is not empty, right? And the tail as well, right? You can only tail out a non-empty record. So how do these things move? How are they animated? So of course, if you know a little bit about how these things typically work, we have a somewhat non-trivial type equality, notion of type equality, which essentially allows type level computation, right? So the tail of a non-empty record type is its actual tail. And so we have a bunch of rules that do the kind of computation that one would expect with these things, and also deal with the refinement bits as well. Okay, these are kinding rules. What about typing rules? Well, we've built the system in such a way that typing is not quite orthogonal, but almost orthogonal to the kinding bits in the following sense. So we have record types, as you probably imagine. And the record types do appeal to kinding in the following way. So if you have a record in the language, right? So the tail of the record is the n bit, and n over there is typed by T2, right? And we need for the record to be well formed, right? So we appeal to the kinding judgment to ensure that indeed the label is not in T2. Okay, so kinding shows up there, and also shows up in this kind case, of course, because we have a kind case construct in the language. And really, all the magic happens in the type conversion rule. Okay, so type conversion is just closure of typing under type equality, right? So if you have a term of a given type U, and you have any type that's equal to U, then M is also of that type, right? And so in essence, the language, the programming language itself, is an ML-looking language, ML-like looking language with references, records, non-terminating computation, right? But the fancy stuff happens essentially sort of one level up. Okay, so we have a tool. So we have a type checker and kind checker, and also an evaluator, right? We have the artifact as available, reusable, and well, the 3 batches. It's about 5,000 lines of code in OCaml. It's quite simple, I guess. And as you probably expect, it offloads the refinement stuff to an SMT solver, which in this case is CVC4. So the types, because we're basically about encoding types and reasoning about types now. So the types are encoded in using values of inductive type in the SMT language. The higher kinded types, we defunctionalize them because you can't really write the function, the type level functions there. And the reasoning about these records is finite sets, essentially. So that's our tool. You can check it out and use it if you dare. In terms of results, more meta theory. So we have a reasonable type theory, we claim. So you have type preservation and kind preservation, if you want to also think of it in those terms. We have progress at both levels. Our type checking is decidable, of course, up to the SMT stuff, which essentially all that put together would mean that, well-typed programs don't go wrong, and I guess well-kinded types also don't go wrong in our language. And so, to conclude, what I tried to show you here, or to give you a little glimpse of, is this fairly simple, I claim, or we claim, framework of type-safe metaprogramming, if you think about it hard enough. And we claim that it's expressive because you can do cool things with it. It's flexible because you can do quite a few things with it. And it's actually simple enough, right? And by that, we also mean that we're doing this on top of a language that is not actually dependently typed or anything like that. The fancy types exist, but it's all sort of hidden in the details one level above. The language itself has non-terminating computation. It has references, all the sort of things people want to have in their programming language. And we have an artifact that is available and you can reuse. So I didn't talk about some things that are in the paper, and there's some points of future work as well. So the kind case allows you to, so this is in the paper, it allows you to write some fancy-ish ad hoc polymorphic functions. We also have a subkinding system because all the kinding stuff is also connected together with subkinding. We don't quite have subtyping in the paper. That's something we're also looking into. Of course, type and kind reconstruction in limited forms is something that we are also looking into. explaining type classes is also kind of interesting in this setting. And also the next move would be to have these sort of meta programs also be stateful in some way, but of course that's potentially complicated. And that's it. Thanks for your time, and I'll take your questions.
Thank you. So if there are questions, please line up here in the front. That's simpler for the logistics.
Hi, I just want to make you aware there's a work, there's actually quite a few papers done in late 1990s and early 2000 along this line. And so my group also have a paper called a Type System for Certified Binaries in POPO 2002 and TOPLUS 2005, where we basically are doing similar things. So the type language is actually CIC, Calculus of Inductive Constructions, so you might check out.
Yeah, which is, yeah. So I would just say that, of course, in our case, part of the focus was also that the type level language has automation built in some sense, which of course, yeah.
So I wanted to ask, have you looked into type inference, and then can you extend Hindley-Milner to work with your...
Hindley-Milner itself, of course, no, because this is a bit more fancy than what you can do with Hindley-Milner. You can do bidirectional typing, and you can go quite a bit with that. But of course, we're looking into the inference part of it, because that's quite important for this to be more usable, let's say.
As far as I understand, you can use your system in order to create automatically very basic constructors for records through this reflection. I was wondering whether you can also create fancier constructors where you say, assuming that I have got something that has to be in a collection, and I don't know what the collection uses in order to put it in the collection, but still I know now that regardless of what it is, when it is created, it will be put in the collection. Perhaps I'm not that clear.
Kind of. So we can do fancier things than the ones I've showed you. For instance, if you have the table lookup that I mentioned is kind of like that, because you have a list of records. You don't know exactly what the shape of the records are, but the thing will still be well typed regardless of the shape. So we can do fancier things, of course. Maybe we can discuss offline, because otherwise, yeah. Sorry.
Okay, let's thank the speaker again. Thank you.